Okay. All right. So we've started talking about the harmonic maps heat flow. So last time what we did is, given a map, say U from M cross 0 epsilon to N, right? We took, using Nash's isometric embedding theorem, we took a smooth isometric embedding of N into some Euclidean space R to the Q. So the embedding was called I. And then we composed our map U with I to get a map U bar from M cross 0 epsilon into RQ. And then we saw that this map U bar, taking values in Euclidean space, this satisfies what's called a nonlinear parabolic PDE. So it's a PDE of the form del U bar del T equal to Laplacian of U bar minus some nonlinear first order differential operator, which we call pi of U bar, du bar, comma du bar, right? Okay. Yeah, where this pi of U bar, du bar, du bar, this was the trace of nabla d pi composed with du bar, du bar. So this was a map from M to R to the Q, where d pi was the nearest point projection defined on a tubular neighborhood of the image of the isometric embedding, right? Is this okay? Yes? Yes, is this all right?
Yes, sir.
Yeah, okay. So what remains to show is that conversely, given a map from M cross 0 epsilon into, say, this tubular neighborhood, N tilde of the image of N in RQ, which satisfies the following two conditions. At time 0, U bar takes values inside I of N, and on M cross 0 epsilon, U bar satisfies this PDE, del U bar del T equal to Laplacian U bar minus this pi of U bar du bar du bar. If U bar satisfies this PDE and it takes values in I of N at time 0, then in fact it takes values in I of N for all T. Okay. And so then we can say that U bar is of the form I composed U, where moreover U is a solution. So U is a map taking values in N, and U is a solution of the heat flow. Okay, the harmonic maps heat flow. So then the point is, we get a one-to-one correspondence between solutions of the harmonic map heat flow and solutions of this PDE, which now has the advantage that it takes values in a linear space inside RQ. Okay, and there we can use some techniques of linear parabolic PDEs. And the idea is to linearize this equation. Okay, and then the linear equation will have solutions by classical theorems. And then you use an inverse function theorem for Banach spaces in order to get a solution for this nonlinear equation. Okay, so that's what we're going to do today. And so therefore, for short time, what we'll get today, what we're going to show is that the harmonic maps heat flow has a solution for some short time. Okay, so we'll get short time existence of solutions of the harmonic maps heat flow. Okay, so that's the goal for today. So the first step is to prove this proposition. Okay, so before that we need a couple of preliminary facts. So suppose first of all, f and g are functions, smooth functions on M. Okay, then we can compute the Laplacian of f times g as follows. So that's going to be the divergence of the gradient of f times g. So by the Leibniz rule, the derivative d of f times g is df into g plus f into dg, right? And so that means the corresponding gradient is going to be the gradient of f times g will be gradient f into g plus f into gradient g. All right. Okay. And so the Laplacian of f times g, this is the divergence of the gradient of f times g. So that becomes the divergence of grad f into g plus divergence of f into grad g. And now we can use the product formula for the divergence, right? So the divergence of grad f into g, that will be a sum of two terms, right? The divergence of grad f into g plus the inner product of grad f with grad g. And similarly, the second term will also give two terms. The inner product of grad f with grad g plus f into the divergence of grad g, right? Is this okay?
Yes, sir.
So what does that give us? Divergence of grad f, this is Laplacian f. So we get the product rule for the Laplacian. This is going to be Laplacian f into g plus twice inner product grad f grad g plus f Laplacian g. Okay. All right.
Yes, sir.
Okay. So now suppose f is a vector valued function, say f1 to fq, taking values in rq. This is what we'll be applying. This is what will come up in our situation. So then we can look at the function norm f squared, right? And we can look at the Laplacian of this. So this would be the Laplacian of summation. So this norm squared is the Euclidean norm squared. So this is summation I goes from 1 to q fi squared, right? And now we can use the product rule for the Laplacian. So this is going to be sum I goes from 1 to q. So I'll get fi Laplacian fi here plus twice inner product grad fi plus fi Laplacian fi. So that gives me twice fi Laplacian fi plus twice norm grad fi squared, right? Okay. Yes.
Yes, sir.
So the first term, this is the Euclid, this is twice the Euclidean inner product of f with Laplacian f, right? Yes. And
Yes,
the
sir.
second term, this I can interpret as twice the norm of df squared. Okay. All right. Yes.
Yes, sir.
Okay. Okay. So that's our formula for the Laplacian of f squared. Okay. So now we can come to the proof of the proposition. So let u bar from m cross 0 epsilon into n tilde in RQ satisfy del u bar del t equal to Laplacian u bar minus, so let me write this term out explicitly. This is actually, the nonlinear term is the trace of nabla d pi of du bar comma du bar. Okay. Right. This is our PD in RQ. All right. So we want to show that u bar takes values in I of n, given that u bar of x0 is in I of n. Okay, for all x in M. Okay, so how can we do this? Well, remember, if this was the submanifold I of n in RQ, then if I took a point, say Z, then I could look at its projection. This was the nearest point projection, pi of Z. And this perpendicular vector, we called rho of Z, right? This rho of Z was Z minus pi of Z. Right? So what we want to show is that u bar belongs to I of n. That's the same as, so a point Z belongs to I of n if and only if rho of Z is 0, right? Yes?
Yes, sir.
Okay, so we want to show that rho composed with u bar is 0. Okay. This is what we want to show. Okay. So therefore, what we can do is look at the function phi of xt is the Euclidean norm squared of rho composed with u bar of xt. Okay. So we want to show this function phi is identically 0. All right. So we know that phi of x comma 0 is 0, right? By hypothesis. All right. So we want to show for all positive time t, this is also true. Phi of xt is 0. Okay. So the idea is going to be that we will look at the time derivative of, so for any time t, I can look at the integral of phi xt d vol m. So it's an integral in the space variable over the manifold M. The claim is that the time derivative of this is less than or equal to 0. Okay. So then we will be done, right? Because that means this integral is monotone decreasing, but at time 0, this integral is 0. So therefore, and the integral is non-negative because it's the integral of a non-negative function. So if it's monotone decreasing, then it has to be less than or equal to 0, but it's also greater than or equal to 0. Therefore, it is identically 0 for all time t. And then because the function phi is non-negative, that means that phi is identically 0 for all time t. So then we're done. Okay. Is it clear?
Yes, sir.
So it's enough to prove this claim, right? So this claim will be a computation, right? So this derivative of this integral is what? By differentiation under the integral sign, this is the integral of del phi del t d vol n, right? Okay. So we have to compute del phi del t. Now, phi is the norm squared of rho composed u bar. So del phi del t, this is del t of inner product rho composed u bar, rho composed u bar. So by the Leibniz rule, this is twice the inner product of del t of rho composed u bar, inner product rho composed u bar, right? So by the chain rule, del t of rho composed u bar, this is d rho of del u bar del t. Okay. And now we can use the fact that u bar is a solution of the given PDE. So del u bar del t, I can write as Laplacian u bar minus trace of nabla d pi composed with du bar. Okay. So all right up to here?
Yeah,
Okay.
yeah, it's all.
Fine. So now what we can do is we can also compute the Laplacian of phi. Okay. So Laplacian in the space variable of phi. So this is the Laplacian of the norm squared of rho composed with u bar. So we've computed what the Laplacian of a norm squared is for a vector valued function. So this is going to be twice the inner product of Laplacian of rho composed with u bar, inner product with rho composed with u bar, plus twice the norm squared of d of rho composed with u bar, right? Yes, this is the formula we just derived.
Yes, sir.
So now, what is the Laplacian of rho composed with u bar? So that follows from composition formula number 2, right? So that's going to be the trace of nabla d rho composed with du bar, right? Plus d rho of Laplacian u bar, right? Yeah, that's the composition formula. Okay. Yes. All right. Is
Yes,
this all
sir.
right? This
Yes,
is the
sir. Yes,
composition
sir.
formula. Okay, but now note that rho plus pi is equal to identity, right? In RQ. So nabla d rho, this we already noticed last time, plus nabla d pi, this is nabla d of identity, which is 0. Right, the second fundamental form of the identity is 0 because it maps straight lines in Rn in Rq to straight lines in Rq. So that means that nabla d rho is equal to minus nabla d pi. Okay, so we can substitute that here. So here we get twice. So let me write it in this way. So I'll get one term, d rho of Laplacian u bar, inner product rho composed with u bar, minus, so I'll take the 2 outside, minus trace of nabla d pi composed with du bar, inner product with rho composed with u bar. All right. Okay. Plus this twice norm of d rho composed with u bar whole squared. Okay. So this is looking similar to the time derivative that we had here, right? This first term is the same. The second term looks slightly different. Here I have a d rho outside. Here I don't have a d rho in this trace of nabla d pi term. There should be a d rho as well, right? So how do I get that d rho? Well, you observe that for any z in this tubular neighborhood n tilde and w a vector in Rq, right? We know that first of all, rho of z, this is in the orthogonal complement of the tangent space at pi of z, the tangent space to I of n, right? So the orthogonal complement, right? Okay.
Yes, sir.
And so, and d pi at z of w, this belongs to the tangent space to the submanifold, right? Because pi takes values in the submanifold. Okay. And d rho at z plus d pi at z, this is equal to the derivative of the identity at z, which is just the identity. Okay. Thus, the inner product between w and rho of z, this I can write as the inner product. So w I think of as identity applied to w. So this is going to be d rho at z applied to w plus d pi at z applied to w, inner product with rho z. But now this d pi at z of w, this belongs to the tangent space to I of n at pi z, whereas rho z belongs to the orthogonal complement of that same tangent space. So this inner product will be 0, right? So therefore this becomes d rho at z of w, inner product with rho z. Is this clear? Yes?
Sir, D rosette lie in the tangent plane, right?
No. D pi z lies in the tangent space, right? To the submanifold.
Okay. Okay. Yes. Okay. Okay. Yeah. It's fine.
Right? Because pi takes values in the submanifold, so its derivative is going to take values in the tangent space to the submanifold.
Yeah. Okay.
Right? So yeah, is this okay now?
Yes,
Yeah.
sir. Yes.
And rho itself is a vector valued function which takes values in the orthogonal complement to the tangent space. So d pi of w and rho of z are orthogonal, so this term vanishes. Okay, so you're left with just this. All right.
Yes, sir.
Is this
Fine. Yes,
yeah?
sir. It's fine.
Okay. So now we can apply that to this term here. I think of this trace of nabla d pi. This whole thing is my w, right? This whole thing is my w. My z is u bar. So this becomes rho of z inner product with w. That I can write as inner product of d rho of w with rho of z. All right. So therefore, this I can write as 2 times inner product of. So I have a d rho here as well. All right. So I'll get what? Laplacian u bar rho composed with u bar minus inner product of d rho of trace of nabla d pi du bar inner product with rho composed with u bar. Okay. Plus twice norm d rho composed with u bar squared. Is this all right? Yes.
Yes, sir.
So now this d rho I can take common to these two terms. So that will give me exactly del phi del t, right? And then I have this extra term, which is non-negative. Okay. All right.
Sir, in the previous line, so can you please repeat how did you get the second term?
What second term?
I mean,
This one.
minus inner product D rho trace of.
Yeah, but just using what I just did right here. The inner product of W with rho Z is the same as inner product of D rho of W with rho Z. So my
Okay.
W is
All
this
right.
whole thing. This whole thing is
Okay.
my W. My U bar, this is my Z. I'm just using that here.
Okay, sir. Yeah, got it.
That's why I did all this over here, so that I could bring this D rho inside. Once I've got the D rho, then I can take the D rho common, and inside I'll get Laplacian U bar minus trace of nabla d pi du bar, etc. And that is exactly what I computed was del phi del t, right?
Yes, sir. This is fine.
Okay. So therefore we get that the integral of del phi del t d vol m over m. So this del phi del t is therefore Laplacian phi minus this twice norm of d rho composed with u bar whole squared. And as we've seen many times before in the course, the integral of the Laplacian over a closed manifold is what? Laplacian of a function integral over a closed manifold, what does that give you?
This 0, right?
Why?
Because I mean phi is 0 on the.
No.
I mean divergence of phi is 0 on the boundary, right?
There is no boundary is the point.
Yeah.
Point is the boundary is empty, right? So by the divergence theorem, it is 0, right? Okay. Yes.
Yes, sir.
Yeah. So So this first term vanishes. So this becomes just minus 2 times the integral over m of norm d of rho composed with u bar squared d vol n, which is less than or equal to. So this is, so by divergence theorem, since boundary m is empty, and this is less than or equal to 0. Okay,
Yes, sir.
all right. So this proves the claim, and so that proves the proposition, right? More or less. So let me just write out the last few steps. So thus, for all t in 0 epsilon, integral of phi xt d vol over m is less than or equal to integral over m of phi x0 d vol, which is 0. So that implies that phi is identically 0. So u bar of xt is in In for all xt, and that means that there exists a smooth map U from M cross 0 epsilon into N such that U bar is equal to I composed with U. All right. And then by previous calculation, we have that so if we look at the previous calculation that we did, what we got is that yeah, so this del u bar del t minus Laplacian u bar. This is minus this trace plus di of this. So taking this term to the other side, what we'll get is that di of let me just see what the signs are. Where is this? Yeah, di of del u del t minus tau u. This will be, yeah, this. Oh, sorry. Yeah, so di of del u del t minus tau u, this will be equal to del u bar del t minus Laplacian u plus trace of nabla d pi du bar du bar. Okay. And this is equal to 0, right? Because by hypothesis on u bar, right? this right hand side. Yes, that's what we're assuming U bar. Okay. So yeah, let's continue. So we get that this U bar takes values in I of n, and therefore it is equal to I composed U for some smooth map U, which takes values in n. And then the equation U bar equal to I composed U. If you differentiate this, what you'll get is that di, this is calculation we did last time, di of del u del t minus tau u is equal to del u bar of del u bar del t minus Laplacian u plus trace of nabla d pi composed with du bar. And this is equal to 0 by hypothesis on U bar, right? Yes?
Yes, sir.
But that means that di of this del u del t minus tau u is 0. But di is injective, right? Because I is an embedding. So that implies that del u del t minus tau u is 0. Okay? All right. So that finishes the proof. Is this okay?
Yes, sir.
Okay. All right. Okay, good. So now we have, therefore, so we have a one-to-one correspondence between maps U from M cross 0 epsilon into N such that del U del T is tau U. So solutions of the harmonic maps heat flow, and maps U bar from M cross 0 epsilon into N tilde in R cube such that del U bar del T is Laplacian U bar minus a trace of nabla d pi du bar du bar. Okay. Fine. Yeah. So let's call this PD A and let's call this PD B. Okay. So we have a one-to-one correspondence between solutions of A and solutions of B. Is this clear? Yes? Yeah, the correspondence is U goes to U bar, which is I composed with U. Okay?
Yes, sir.
Okay. So, I mean, here the one thing I should say, yeah, the U bar such that this, and at time 0, it takes value in I of n. Okay, so maybe I should say that. So, yeah. And U bar of x0 belongs to I of n for all x in n. Okay. So what we're actually going to prove is short-term existence for solutions of this equation in R cube. Okay, that's what we're going to prove. And as a consequence, we'll get short-term existence for solutions of the harmonic maps heat flow. All right.
Yes, sir.
Okay. So what do we do then? So we're going to need to introduce what are called certain Banach spaces called Holder spaces. Okay. So the definitions are a bit long, so I'm just going to read through the notes for that. So all of you know what an alpha Holder function is, right? From a metric space to another metric space. Yes. That means that d of fx fy is less than a constant times b of xy power alpha, right? Where alpha is in between 0 and 1. Okay. Yeah, that's
Yes,
called
sir.
alpha Holder map, right? So it's going to be convenient to work in certain Banach spaces where you look at functions which are, let's say, C2, and also the second derivatives are Holder functions. So that gives some extra control. So for example, if you have a sequence of uniformly Holder functions, so that means the constant C which occurs in the Holder inequality, right? dfx fy less than or equal to C times dxy power alpha. That best constant C is called the Holder norm. So if the Holder norms of a sequence of functions are uniformly bounded, then the functions are equicontinuous, right? Yeah, that's clear to see.
Yes, sir.
Equicontinuity if the Holder norms are uniformly bounded. And also, therefore, by the Arzela-Ascoli theorem, if the Holder norms are bounded and also the sup norms are bounded, so suppose my functions are taking values in Rq. So if the sup norms are bounded and the Holder norms are bounded, then by the Arzela-Ascoli theorem, there will be a uniformly convergent subsequence, right? Yeah. Okay. And so the idea is if you have functions which are C2 comma alpha, that means twice continuously differentiable, and the second derivatives are alpha Holder. Okay. So then if you have a bounded sequence in C2 alpha, what that will mean is that the sup norms of the function, its first derivative and second derivative, these sup norms are all bounded, and also the alpha Holder norms of the second derivatives are bounded. Okay. So if you have such a bounded sequence in C2 alpha, what that will mean is that the second derivatives are uniformly bounded because the C2 norms are bounded, but also the alpha Holder norms of the second derivatives are uniformly bounded. So therefore, the second derivatives will become equicontinuous and uniformly bounded. Therefore, they will have a subsequence which converges uniformly. Okay, so the second derivatives will converge uniformly. So that will mean that, I mean, you'll have a subsequence which converges in C2. Okay. So the idea is that a bounded sequence in C2 alpha will be pre-compact in C2. Is that clear?
Yes, sir.
Okay, that's the idea. So boundedness in C2 alpha, that's what we're going to show eventually for solutions of the heat equation, this nonlinear PD, or for the harmonic maps heat flow. That will imply pre-compactness in C2 norms. So you'll get a subsequence which converges in C2. Okay. All right. So let me get to the definition. So suppose U is first we're going to look at solutions of PDs with a space variable in M and a time variable. So those will be functions defined on this manifold Q, which is M cross close 0, 1. Okay. So we're going to define Q to be this, M cross close 0, 1. Then we take an alpha in between 0 and 1. Now, if I take a function u from capital Q into RQ, then we let, first of all, the norm u sub q. This is just the sup norm. Okay. So this is the sup over xt in q, norm of uxt. Okay. Then we define a sort of partial holder norm with respect to the space variable. Okay. So this is going to be bracket u sub x super alpha. So this is like a partial derivative in a sense. So what you do here is you take the sup over x comma t and x prime comma t in Q, where x is not equal to x prime. And then you look at the norm of uxt minus ux prime t and divide this by the distance xx prime power alpha. Okay. So this defines a semi-norm on functions, right? Okay. So we're taking a holder norm in the space variable only. So the t is the same here. Only x and x prime are different. All right. Similarly, we can define a partial holder semi-norm in the time variable. So then we're going to take x comma t and x comma t prime, where t is not equal to t prime. And then you look at the sup of norm of uxt minus uxt prime divided by mod t minus t prime power alpha. Is this clear? All right.
Yes, sir.
Okay. So now we're going to define certain holder norms which have a coefficient in the space variable and in the time variable, which are slightly different. So it turns out the right coefficients to look at are this, where the holder index in the space variable is twice the holder index in the time variable. Okay. That's because you're taking two space derivatives versus one time derivative in the heat equation. So it turns out the right holder norms to look at are alpha in the space variable and alpha by 2 in the time variable. And similarly, we will look at a norm C2 plus alpha and C1 plus alpha by 2. So this will mean 2 plus alpha means 2 space derivatives and the second derivatives are alpha holder. Okay, the second derivatives in the space variable are alpha holder, whereas 1 plus alpha by 2 means one time derivative, and that time derivative is alpha by 2 holder. Okay, so that's what this notation means. All right. So let me define these norms. So the norm alpha comma alpha by 2, this is norm uq, that's just the sup norm, plus the alpha holder norm in the x variable, in the space variable, plus the alpha by 2 norm in the time variable. Okay, so this is straightforward. All right. This one, the next norm is a bit more complicated. This is the 2 plus alpha comma 1 plus alpha by 2 norm. So first we're going to have the sup norm of the function, then the sup norms of the first derivatives. So the norm of del tu sup norm, and then the norm of dxu sup norm. Okay. Now, I just have to clarify something here. What is dxu? That's the derivative in the space variable. So that I want to think of as a map defined on a compact manifold, right? So in order to take its supremum, so the compact manifold is going to be what's called the unit tangent bundle of M, T1M. That means the set of all unit tangent vectors in M, okay? So notice that since dxu this is a linear map on each tangent space, it's determined by its restriction to the unit tangent bundle, right? So if the restriction to the unit tangent bundle is 0, then the derivative is identically 0, right? Okay. So dxu is a function on the compact manifold T1M taking values in RQ. X comma V goes to the derivative in the space variable dxu at x comma t applied to v. Okay. Is this clear?
Yes, sir.
And what is the second derivative? D squared xu. So the second derivative is given by the second fundamental form in the x variable, nabla du. Now, nabla du, this is a symmetric bilinear form taking values in RQ. So it is determined by its values along the diagonal, right? And the values along the diagonal, again by homogeneity, they're determined by the restriction to the unit tangent bundle, right? So if this d squared u, so this is defined to be acting on x comma v, an element of the unit tangent bundle. This is nabla du at x comma t applied to v comma v. Okay. So if this is 0 identically, then nabla du will be identically 0, right? Okay. Okay, so when I look at this supremum of dxu q, this is actually a supremum over the unit tangent bundle cross the closed interval 0, 1. So that's a compact space. Okay, so this supremum makes sense if my function is C1, all right, in the space variable. Is that clear?
Yes, sir.
And similarly, if the function is C2, then this norm of d squared xu, this sup norm, this also makes sense, right? This will also be a function on T1n cross close 0, 1, a continuous function. Okay. So I want my function to be C2 in the space variable. And then this is basically its C2 norm in the space variable, right? This norm u plus norm dxu plus norm d squared xu. And then I am also taking a C1 norm in the time variable. Okay, fine. So that gives what would be called a C2 comma 1 norm. So C2 norm in space variable and C1 norm in time variable. That's what the first 3 terms are. Is that clear? The first 4 terms. This is a C2 comma 1 norm. All right. Yes.
Yes, sir.
Okay. But now I have this extra alpha and alpha by 2 in the space and time variables. So what that is going to mean is that I'm going to take the alpha by 2 norm, alpha by 2 Holder norm of the first, okay. So I take the first time derivative, del tu. So this thing, I'm going to take its alpha by 2 time Holder norm and its alpha x space Holder norm. Okay. So these 2 terms I'm going to take. And then for the first derivative, dxu, I'm going to take its in the time variable, the Holder norm half plus alpha by 2. Then in the space, and then for the second derivative, I'm going to take the alpha Holder norm in the space variable and the alpha by 2 Holder norm in the time variable. Okay. Is this all right? So it's a bit complicated, but not too much. Okay. Is this okay?
Yes, sir.
Okay. All right. So that's the definition of these Holder norms. And then we can define the Holder spaces. So the C alpha comma alpha by 2 Holder space for maps from Q into RQ is the set of continuous functions U from Q into RQ such that this alpha comma alpha by 2 Holder norm is finite. Okay. So that means it's going to be alpha Holder in the space variable and alpha by 2 Holder in the time variable. Okay. All right. So this space is rather straightforward. And this, the other space is C2 plus alpha, comma 1 plus alpha by 2, Q comma R2, Q comma RQ. So that will mean functions which are C2 comma 1 from Q comma to RQ. So 2 comma 1 means it's C2 in the space variable and C1 in the time variable. Okay. And here you want this rather complicated norm, the 2 plus alpha comma 1 plus alpha by 2 Holder norm. This should be finite. So in particular, what this means is that if you look at the definition, if you look at the second derivative is alpha Holder in the space variable and alpha by 2 Holder in the time variable. Okay, so if this Holder norm is bounded, this 2 plus alpha comma 1 plus alpha by 2, that means the second derivatives will be equicontinuous, right? The second derivatives will be equicontinuous. Is that clear?
Yes, sir.
Okay. Fine. So maybe now, yeah, so we define these spaces. So these Holder spaces are Banach spaces, okay? That one can show, that's not too difficult. And one can also look at a subset of this second Banach space of maps which take values in n, right? So these are the functions u in C2 plus alpha, 1 plus alpha by 2 from Q to RQ, such that u of q is contained in n, where n is identified with its image in RQ, I of n actually, okay? So, well, I mean, well, this I can define for any subset n of RQ, any closed subset. This space will be a closed subspace of, not a linear subspace, just a closed subset of this Banach space. Okay. All right. Why am I doing all this? Because we want to use the following result, which is a classical result for what are called linear parabolic operators. So a linear parabolic operator means that it's a linear differential operator where it's of second order, where the second order term is just the Laplacian. And in the space variable, and in the time variable, it's minus the time derivative del t. Okay, so there is this, actually this Laplacian delta minus del t, this is called the heat operator. Okay, so it's an operator in both space and time. It's called the heat operator, right? So you have this Laplacian u minus del t u, and then you have some first order and a 0th order term. Okay. So take such an operator. What does it act on? It acts on maps u, which are from Q into RQ. All right. So these are C2-1 maps. Okay. So u is a vector valued function. Okay. So this LU, this is a vector. So this Laplacian u is a vector in RQ. This del tu, del u del t, this is a vector. So this A dot grad u, this is actually a vector. It's not a scalar. And this B dot u, this is also a vector. So how is this defined? This A dot grad u means the following. A is given by a Q tuple of matrices, A1 up to AQ. See, U is a vector valued function. So grad U is actually a matrix. All right. Grad U is actually a matrix. Okay. Or a linear map. So this A dot grad U means the vector which is trace of A1 star grad U up to trace of AQ star grad U. Okay. This trace of AQ star grad U, this is inner product of the linear maps A1 and grad U up to the inner product of AQ and grad U. All right. So this takes values in RQ. And similarly, B dot U, B is given by a map from the manifold Q into, it's a tuple of vectors. So B1 is a vector in RQ up to BQ is also a vector in RQ. And this B dot U is the vector in RQ whose coordinates are inner product B1U up to inner product BQU. Okay. Is this all right? So those are the first order and the 0th order terms. And what we assume is that the coefficients of the first order and 0th order terms, these are in the Holder space alpha comma alpha by 2. Okay. So the coefficients are in the Holder space alpha comma alpha by 2 for some alpha in 0, 1. Then the theorem says for any capital F in the Holder space alpha alpha by 2 from Q to RQ, and for any map F which is C2 plus alpha from M into RQ. So 2 plus alpha means that it's C2 and the second derivatives are alpha Holder. Okay. Then this theorem says there is a unique solution U in the space C2 plus alpha comma 1 plus alpha by 2. So this is exactly the space we defined. So this U is the unique solution to the initial value problem. So the problem is LU of xt is f of xt for xt in M cross 0, 1, and U of x comma 0, this is the initial value, is equal to f of x for x in M. All right. So this initial value problem has a unique solution. All right. And moreover, we have an estimate on the norm of the solution. So the 2 plus alpha comma 1 plus alpha by 2 Holder norm of the solution is less than or equal to a constant times the sum of the alpha comma alpha by 2 Holder norm of F, capital F, plus the 2 plus alpha Holder norm of little f. Okay. Is this all right?
Yes, sir.
So essentially what it's saying is that for linear parabolic PDEs, vector valued linear parabolic PDEs with Holder coefficients, we get a unique Holder solution. All right. That's what it's saying. I mean, a unique solution in the appropriate Holder space. Okay. 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 So this is going to be the main tool that we're going to use now. So let me explain how we're going to use this. All right. To prove the short-term existence. So short-term existence for the heat flow. So there are going to be quite a few steps. So let me try and explain. Okay. So what are we given first of all? So we're given an initial data. F is a map from M to N such that F is C2 plus alpha. Okay. All right. So you fix an alpha in between 0 and 1. So you're given an initial data F. Now you want to construct a solution of the heat flow with this initial value, right? Okay. So you let F bar be I composed with U, right? So this goes from M into I of N, which is sitting inside RQ. All right. Now, what do we want? We want a U, which is going to be C2 plus alpha, comma 1 plus alpha by 2. Defined on some M cross some small time 0 epsilon. Okay. Mapping into RQ such that this initial value problem holds. So I don't know what to call it. Let me call this sorry, this should be I composed with F, not I composed with U. It's I composed with F. Sorry. Okay. So let me just call this D. Okay, fine. This initial value problem. So the initial value problem is the initial value is U of X comma 0 is F bar of X, right? For all X in M. And we have this PD del U del T is equal to Laplacian U minus that. So let me write it in this form. Del U del T minus Laplacian U plus trace of nabla d pi of du. So I've changed notation a bit. Earlier I was calling the map taking values in RQ, I was calling that U bar. But I'm just, for simplicity, I'm just going to call that map U, okay? But this is a map taking values in RQ, all right? Okay. So I want this equal to 0, right? Xt in M cross 0 epsilon. Yeah, this is what we want, right? Yes?
Yes, sir.
Okay. Now, the idea is you look at this first, this operator, this differential operator, right? And you call that, so this we can think of as a map between Holder spaces actually. All right. So the first thing is that this d pi is a bit of a problem because pi is only defined on the neighborhood n tilde, right, of I of n. So the first step is you extend pi. So pi is defined on n tilde, right? So extend it to a smooth map which I will also call pi from all of RQ to RQ, okay, such that pi is identically constant equal to 0 outside some bounded neighborhood of I of n. Okay, so how can I do this? I just take my map pi and multiply it by a bump function, right? Which vanishes outside a small neighborhood of I of n. Is that clear?
Yes, sir.
Okay, so you multiply pi by some bump function phi in CC infinity of some n tilde. Okay. All right, such that okay, yeah, okay. No, this is fine. Such that phi is equal to 1 in a neighborhood of I of n. Okay, so that gives me an extension. Okay. So then the point is that then for all k, the kth derivatives of pi are bounded on RQ because it's constant outside a compact. Okay. All right.
Yes, sir.
Okay. So now our pi is defined everywhere. So now we can define an operator, right? Between, this is going to be a map between Holder spaces, right? So now we can define so my pi is globally defined now. So therefore I can define a map P. So where is this going to go from? From C2 plus alpha, comma 1 plus alpha by 2 of M cross 0, 1 RQ. 2, this is going to take values in C alpha, comma alpha by 2 of M cross 0, 1, comma RQ. Okay. This is the map. U goes to Laplacian U minus del U del T minus trace of nabla d pi du du. Okay, now this is defined for any map U, right? It doesn't have to take values in the tubular neighborhood of I of n, right? It can take values anywhere in RQ. Okay, so this is a well-defined map. Okay. What one has to check is that actually it takes values in this Holder space. But yeah, I won't do that. Okay, so because, well, yeah. So I mean, this Laplacian U, this is a second derivative of U, and this is in the space C2 plus alpha. So, I mean, the second derivatives are alpha Holder. So that means this Laplacian U in the space variable will be alpha Holder. Okay. And then you can check the other terms also belong to the right space. Okay. Okay, so we have this map between Holder spaces. All right. So what we want is U such that U of x0 is identically equal to f bar of x, and such that, so if I look at P of U, right? So this is defined on M cross 0, 1. All I want is that restricted to M cross 0 epsilon, for some epsilon, this should be identically 0, right? All right. This is what I want, then I'll be done, right? Yes.
Yes, sir.
Okay. So how do we do this? So step 1. So the idea, the idea is you look at this, where P is taking values, this alpha comma alpha by 2 holder space. So this is maps defined on M cross 0, 1, right? So I can think of it as a 1 parameter family of maps, right? From M to RQ, right? So if I call P of U, if this is equal to a family of maps, let me call this, say, V sub T. So let me call this V, and V is given by a family of maps, V sub T from M to RQ, right? Where T goes from 0 to 1, all right? Right, V sub T of X is V of XT, okay? Right? So I can think of this as a curve in the space of maps, right? Yes.
Yes, sir.
Okay. So what I have is the following. So here is my time variable. And here, so in the space variable, these are going to be alpha holder. So this is C alpha M RQ. Well, no, it's not a graph. Okay, fine. How do I put this? So, no, okay, fine. Yeah. Oh, I can write. Okay, I can write it. So let me draw it like this. So C alpha M RQ. So what I want is something which is identically 0, right? So what we will do is step 1. Is you construct U naught. So this will be an approximate solution to this problem such that P of U naught equal to V, where just V0 is equal to 0. Okay, so what I want is Vt equal to 0 for all t in some 0 epsilon, right? But I'm going to first construct an approximate solution. So U naught will be an approximate solution. Okay. So then what I get is I get a curve which starts at 0, right? And then it takes some values in this space of maps. Okay. So this is my, so at time t, this is my Vt. Okay. All right. And this is V0 is 0. Okay. All right. Yes.
Yes, sir.
Yes, sir.
Okay. So I'm just constructing an approximate solution first. So this actually is not hard to do, because what we can do is the following. How to do this? So we do this as follows. We use the classical theorem on linear parabolic PDEs. You let U naught be the solution of the initial value problem for the linear parabolic PDE. Well, what is the linear parabolic PDE that we need to look at? Well, the PDE that we're looking at is this, right? Del U del T minus Laplacian U plus trace of nabla d pi du equal to 0. So this is the nonlinear term is only this term, right? This last term, trace of nabla d pi du. So it's nonlinear because there's du occurring twice, right? So, but what happens to this at time 0? At time 0, this u is going to be f bar. So this du is going to be df bar, right? So I can, at time 0, I can replace this by df bar, right? Then this becomes something which is independent of u, right? So this part, so then I can take this to the other side, and then I will get a linear parabolic PDE, right? So the linear parabolic PDE will be del u naught del t minus Laplacian u equal to minus trace of nabla d pi of df bar comma f df bar. Okay, so this right hand side, this is my capital F in the theorem on linear parabolic PDEs. All right, this is my capital F. Is that clear? This is my operator LU. It's just the heat operator. Okay.
Yes, sir.
So this is a linear parabolic PDE. So this will have a solution given what is my initial condition. U naught of x0 is f bar of x. Okay. So this has a solution, right? By the classical theorem on linear parabolic PDEs, right?
Yes, sir.
Yeah. And so this solution exists by the classical theorem. Okay. U naught exists by classical theorem. And satisfies if I look at P of U naught equal to V, which is say Vt, T in 0, 1, where such that what is V naught? So V naught is going to be my nonlinear thing at time 0. So that is del U naught del T minus Laplacian U minus trace of nabla d pi du bar du bar, the whole thing at time t equal to 0. At time t equal to 0, du bar, du naught bar, du naught, sorry, not u bar, sorry. This is u naught, du naught, du naught. Laplacian u naught. So this thing is equal to del u naught del t minus Laplacian u naught minus trace of nabla d pi df bar, right? At time t equal to 0, right? Which is equal to 0 by construction. All right. Sorry, this should be a plus sign. Yeah, plus. Is this okay?
Yes, sir.
Yes.
Okay, so this satisfies V naught equal to 0. Now we want to perturb U naught so that we get something where Vt is identically 0 for t in some small interval, 0 to epsilon. Okay. So here is this is a next crucial step. Step 2. Okay, step 2 is the following. Let V be an element. So I'm going to write it as a curve, Vt, t in 0, 1. A curve in the space of maps from M to RQ. So this is an element of C alpha, comma, alpha by 2. M RQ. Then what we can do is the following. So let this be such that V naught is equal to 0. Okay. So now let zeta from R to R be a smooth function such that zeta is equal to, so such that zeta is in between. So let me just say it takes values in 0, 1. Okay. Yeah. So what happened? Yeah. So zeta takes values in 0, 1. Such that, so zeta is identically 0 on the interval -infinity to 1, and zeta is identically 1 on the interval from 2 to infinity. Okay. So this is just a function of time. You think of zeta as a function of time t. So the graph of zeta looks like this. Let me define and let zeta sub epsilon of t be zeta of t over epsilon. Okay. For epsilon positive. So what will the graph of this zeta epsilon look like? If this is time t, then basically if this is epsilon and this is 2 epsilon, then zeta epsilon looks something like this, right? Is that clear? Yeah, this is the graph y equal to zeta epsilon of t. Yes?
Yes, sir.
Yeah, this is 1 here. Okay. So what I'm going to do is I'm going to multiply I let v tilde of x comma t now, I let this be zeta epsilon of t into v of xt. Okay. So that means, so v tilde is also an element of the Holder space. Okay. So v tilde is some v tilde t, where what is v tilde t? This is equal to zeta epsilon of t into vt, right? Okay. So this is in C alpha alpha by 2 M RQ. Okay. So why am I doing all this? Because now this V tilde is going to be 0 on the interval from 0 to epsilon, right? Oh, sorry. No, I've got it the other way around. I've got it the other. No, wait. No, this is correct. Let me just check my notes. This is correct. Yeah, this is correct. This is correct. No, this is wrong. Okay, sorry. I got it the other way around. No, sorry. Okay, I got it the other way around. Yeah, okay. All right. Yeah, so yeah, okay. So fine. No, I got it the other way around. Let me just this. Sorry, this is 1 here and 0 here. Sorry, I got it the other way around. Okay. So, sorry, the graph is going to be like this. It's 1 up to here, up to epsilon, and then 0 here. Yeah, okay. So, so what does this look like? It means that if this was my t, if my vt, so this was my v0, right? V0 was 0. So my vt looks something like this, right? It could be something. If I multiply by this zeta epsilon of t into vt, what's going to happen? This is 1 up to time epsilon and then 0 after time 2 epsilon, right? So this is epsilon, 2 epsilon. So I'm going to follow the same graph up to this time, and then I'll slowly multiply by something going to 0. So then I'll get something looking like this, which, oh, sorry, what am I doing? Sorry, it's going down to 0. So that means it'll go down to 0 like this. Okay. Yeah, so this is my Vt and this is my V tilde t. Okay. All right. Is the picture clear now?
Yes, sir.
Yeah, so it follows Vt up to some time, and then after time 2 epsilon, it becomes 0. Okay. So the point is, what you might expect from this picture is that the Holder norm of this V tilde will be small if epsilon is small, right? So actually that happens if you do a small trick. So if you let alpha prime be a number strictly less than alpha, okay, then what one can show is that there exists a constant C positive such that if I look at V tilde, then if I look at the alpha prime comma alpha prime by 2 norm of this is less than a constant times epsilon to the power alpha minus alpha prime by 2 into the Holder norm of V alpha by 2. Okay. All right. So I don't think I have time to prove this today. You can look in the notes, it's done here. It's just an elementary thing. So this is the lemma here. All right. This is the lemma here. So my notation is a little different. I'm calling that V tilde some W epsilon of xt. It's the same thing, zeta epsilon of t into W of xt. All right. My hypothesis is that W at time 0 is identically 0. And then the point is that as epsilon tends to 0, the alpha prime comma alpha prime by 2 norm becomes very small. Okay. All right. Okay. So the proof is just straightforward. It's very elementary. There's nothing here. You can look at the proof. All right. I don't have time to do it. Okay. It's a bit long, but it's elementary. All right. So what is the consequence of this? The consequence is the following, that now if I look at the difference, if I look at V minus V tilde, so yeah, so my notation is a bit different from the class than from the notes. Let's just go with the notation here. So the point is then if I let W to be V minus V tilde, okay, then so this W is some WT. Okay. So then the first thing is that since V tilde is equal to V for t in the range 0 to epsilon, that means that WT is identically 0 for t in the interval 0 to epsilon. Okay. Secondly, the norm of WT is as small as the W is as close to V as we want, right? The norm of V minus W, if I look in the alpha prime comma alpha prime by 2 norm, this is less than a constant times epsilon to the alpha minus alpha prime by 2 into this norm. So this norm is some constant. So let me make it some other constant, C prime into this. Okay. So what is the upshot? The upshot is that if I take a V, so that at time 0, V naught is equal to 0, right? Then what I can do is basically I'm getting a W. So W will look something like this. It's going to be 0 up to time epsilon. And then it's going to, so if this is my VT, my WT is going to look like this. It's going to look like this. Yeah, so this second graph, this is WT. And this graph is VT. Is this clear? Yeah.
Yes, sir.
Yeah, so the point is, I can get a W which is as close to V as I want, but now my W is 0 on a small interval, right? My W is 0 on a small interval. Okay. And finally, we have step 3, which is to use the inverse function theorem. For the map P, the nonlinear map P, which was going between two Holder spaces. So the idea is that you define certain subspaces of the Holder spaces. X is the set of U in C2 plus alpha 1 plus alpha by 2 M RQ, such that let me just check. Yeah, so yeah, actually alpha prime. Okay, so at time 0 is 0 and time derivative is 0. Okay, fine. So let me call it Z. Yeah, so alpha prime and 1 plus alpha prime by 2. Okay, so Z at time 0, Z naught is 0, and del ZT del T at time 0 is 0. Okay. So this is a closed subspace of my Banach space. This is also a Banach space. Okay. And then you have Y, which is the set of K in C alpha prime, comma alpha prime by 2 M RQ, such that K naught is 0. Okay. All right. And then what happens is that you define a map. So we're given U in U naught, we're given our U naught, right? In C 2 plus alpha, comma 1 plus alpha by 2 M RQ, such that P of U equal to V in C alpha alpha by 2 M RQ, such that V naught is equal to 0, right? Yeah. So then we define a map script P from the Banach space X to the Banach space Y, which is Z goes to P of U naught plus Z minus P of U naught. Okay. All right. So P of 0 is 0, clearly, right? Script P of 0 is 0. And what one has to check is that this takes values in Y, okay, where this K naught is 0. So you can check that. It's not too hard to check. So I mean, that's because, see, if Z belongs to X, then P of Z is, so this is P of U naught plus Z. So what's that going to be? So, so Laplacian U naught plus Z. So I have to look at, so this at time 0, right? T equal to 0. So, okay, Laplacian U naught plus Z minus del T U naught plus Z minus trace of nabla d pi of D of U naught plus Z D of U naught plus Z. This thing minus nabla U naught minus, yeah, del T U naught minus trace of nabla d pi d U naught d U naught, right? The whole thing at time t equal to 0. I have to check that this is 0 at time t equal to 0, right? In order to say that I take values in the Banach space Y. Banach space Y is where my the space of curves which are take the value 0 at time 0, right? So here this nabla delta of U naught plus Z, delta U naught will cancel. I'll get delta Z, but Z is an element of the Banach space Y, or X, sorry. Z is an element of the Banach space X, where at time 0, Z naught is 0, right? So that means as a function of the space variable, it's 0. So its Laplacian is 0, right? So this delta Z term will become 0. Delta U naught will cancel. And also this del T U naught, del T U naught will cancel. Del Z del T at time 0 is 0 by hypothesis, because I'm in the Banach space X, right? Yes, okay. So where are we? And here, this thing you can expand by bilinearity. The du naught will cancel. You'll get a dz du naught, twice a dz du naught. That will vanish because at time 0, z is 0. So the derivative d of z, the space derivative, is also 0. So that will vanish. And similarly, the dz term will also vanish, right? At time 0, the space derivative dz is 0. Is this clear? So this whole thing will be 0. Okay, because Z belongs to X. All right. Is this all right?
Yes, sir. Yes.
Yeah, so PZ belongs to Y. Okay. So this is a well-defined linear map from X to Y. Sorry, not linear, non-linear map. What one checks, what one has to do is actually check that. So this thing is a non-linear operator. It has a linear part which is parabolic, and then this non-linear part, right? But it turns out that you can, it turns out that using, so this dp naught, this map is dp, sorry. Yeah, this map is differentiable, and its derivative at the origin, this is isomorphism of Banach spaces. Okay, this is an isomorphism of Banach spaces. So because this is it turns out that dp naught, this is a linear parabolic operator. Okay. And then the fact that this is 1-to-1 and onto and is bounded, has a bounded inverse, all that follows from the classical theorem on linear parabolic PDEs. Okay. So once you have that, that implies by inverse function theorem that P maps a neighborhood 0 of X onto a neighborhood of 0 in Y. Okay, right? This is by the inverse function theorem for Banach spaces. Right?
Yes, sir.
Okay, good. So how can we use that? Okay, look, there's a minute remaining. If you just give me 5 minutes, I can finish the proof. So can we stop this session and start a new one? I'll just take 5 minutes to wrap up the proof. All right?
Yes. Yes, sir.
Okay, okay. Thank you. So I'm stopping this session and starting a new one. Okay. Okay, so I'm just finishing the proof of this short-term existence. Yeah. So let's recall what was P of Z.
You have to share this.
Oh,
Are you
sorry,
sharing
sorry,
screen share?
Sorry. I forgot to share. 1 second. Sorry. Yeah, okay. Okay, all right. So we're almost there. Yeah. So I have this nonlinear map. P of Z is equal to capital P of U naught plus V minus capital P of V, right? Yeah. Now P of U naught, minus P of U. Minus P of U. Right? Now, so this is equal to P of U naught plus V. U naught plus Z. Or what am I doing? Sorry. Yeah, U naught plus Z. Yeah, U naught plus Z. Okay, minus, this is my V. Okay, now what did I have? I had that V naught I had chosen so that V naught is 0, right? And we found a W in C alpha prime by 2. Yeah, right. So M cross 0, 1, 2 RQ such that norm of V minus W, this is less than constant times epsilon to the alpha minus alpha prime over 2. Yeah. So this is less than some delta. Okay. So let's suppose that in Y, this is a ball of radius delta. Okay. So I map onto ball of radius delta here. So I can choose this epsilon small enough so that this becomes less than delta for epsilon small, right? Okay. And what we had was that Wt is equal to Vt for t less than epsilon, right? Yeah, this is how we chose our W. So then if I let K to be V minus W, or W minus V, sorry, let it be W minus V. Okay, so this is in the ball of radius delta in Y. Okay. Then there exists Z in X such that script P of Z is equal to K, right? And that means that P of U naught plus Z minus V is equal to K, which is W minus V. So that means that P of U naught plus Z is equal to this W. Right? Yeah. And so we are done. We let U be U naught plus Z. Right? This will be our solution. Okay. So this is in C alpha prime 2 plus alpha prime 1 plus alpha prime by 2 Q comma RQ. Okay. Then U of X comma 0. This is U naught of X comma 0, right? Because Z belongs to X. So Z of X comma 0 is 0, right? So this is equal to my F bar of X, right? So my U satisfies the initial value and it also satisfies the PD for time epsilon because W of X comma T, this is 0 for T between 0 to epsilon, right? And what is W? W is P of U. So this is Laplacian U minus del U del T minus trace of nabla d pi du du, right? Okay. So that means
Yes, sir.
time 0 to epsilon, I satisfied the PDE. That's all I wanted, right? That's it. Is this okay?
Yes.
Yes, sir.
Yeah. So yeah, so I mean, so let me just write that PU is equal to W, which is 0 for TU. Okay. So yeah, I don't have many lectures left, so I had to go a bit sketchy on this, but I just wanted to give you the idea of the main steps. Okay. So the main step was you construct the approximate solution. It takes values in some curve which is 0 at time 0. That curve you can perturb a bit to get a curve which is 0 in an interval from 0 to epsilon. That's my W, right? You perturb it a bit so that it becomes identically 0 for time between 0 to epsilon. You can perturb it without changing the alpha prime Holder norm too much. Okay. And then, so the W is close to V. And then because it's close enough to V, by the inverse function theorem for the operator, for the nonlinear operator, right? You get a U which is which maps to W under the nonlinear operator P. And then the W is 0 identically in the interval 0 to epsilon, and therefore you satisfy the PD for time 0 to epsilon. All right. Okay. Yeah, so I mean, pictorially, it's quite simple. You basically, you have here this is your U naught. So it's taking values in space of curves. So this is my capital P. So the initial curve looks something like this. It's 0 at time 0, right? And then you approximate this by some guy which looks like this. It's 0 for time epsilon. Yeah, and you can do this without changing the Holder norm too much. So this fellow is my V, and this guy is my W. Okay, and W is in a ball of radius delta around V. Okay, so by the inverse function theorem, you find a U which is close to U naught, which maps onto W. And that's it, you're done. Is this clear?
Yes, sir.
Okay, so the reason why you can apply the inverse function theorem, that comes from the fact that, so that computation is done in the notes. I don't have time to do it today. But the point is this nonlinear operator, when you differentiate it with respect to Z, what will happen is the linear term stays the same. Okay, so you get this Laplacian minus del del t as part of the derivative. And then this nonlinear term, what will happen is it'll give you a linear operator after differentiating. And that will be first order. Okay, that will be first order. And so what you'll get is a linear parabolic operator. Okay, so this derivative of P at 0, this becomes a linear parabolic operator. And then it's an isomorphism of Banach spaces. It's 1-to-1 onto. That will follow from the uniqueness and existence for solutions of linear parabolic operators. And the fact that the inverse is bounded, that will follow from the estimate given in the theorem on linear parabolic operators, that the norm of a solution is less than or equal to, norm of the image under the operator. So, okay. So that will imply boundedness of the inverse, and then therefore it becomes an isomorphism. Therefore, you can use the inverse function theorem. Okay. So if you want more details, just look through the notes. I don't have time to do this in more detail. All right. Okay. Yeah. Any questions before we stop? Any questions?
No, sir.
Okay. So if you want to remember the proof in one line, just remember this picture. That's enough. Okay. Just remember this picture, and that will tell you. Okay. Yeah. So, I mean, yeah. So I'll just write it here. P of U naught is V. And then you perturb V to W so that you get a U, so that P of U is W. That's all we're doing here. Okay. All right. Okay. All right. So let me stop here and we'll continue next week.